Thanks a lot. Good evening, everyone. I would first like to thank the organizers for inviting me here to this wonderful event, which is all about nuclear technology and nuclear innovation. But I want to take you one step deeper, and I want to discuss with you the field of elementary particle physics, which is the field of subnuclear or subatomic particle physics. Now, the question that I have to ask myself during my everyday research is the following. What are the fundamental building blocks of the universe? So what is basically everything made of? And it's a question not only I ask myself. People have been asking that question for many, many centuries in the past. And it actually dates back to 400 before Christ already, when there was a Greek philosopher who was named Democritus, and he was the first to ask this question. What happens if you split matter into smaller and smaller and smaller pieces? Can you keep on doing that infinitely, or is there a point at which you actually reach a fundamental constituent of matter? That's a very good thought experiment. And so let's have a look at what we know today about the structure of matter. Let's start with something we're familiar with. Why not take our cells as an example? We are ourselves made up of smaller parts, which we call cells. I put here a brain cell, a very important one in my field, of course. So these cells, they are themselves composed out of molecules, and molecules are then again composed out of atoms. Now you may remember from your high school studies that an atom is composed out of a core, a nucleus, which we call it, and around it are surrounding electrons. And as far as we know today, and I find that always important to mention, as far as we know today, these electrons are indeed fundamental constituents of matter. We call them elementary particles, which means they have no further substructure. We cannot split them into smaller pieces. However, if you look at this nucleus here in the middle, this is composed out of smaller parts. These are composed out of protons and neutrons, and they are made up of quarks, up quarks and down quarks. And indeed, such quarks are indeed, as far as we think today, again, fundamental particles. And so what that learns us is that we basically only need three constituents to build all matter. We need up quarks, down quarks, and electrons. And that allows us to build all atoms, the table of Mendeleev, let's say, and so all matter in the universe. Well, our research, it has shown us that there are slightly more particles we have discovered. So there are some heavier particles, but they're also typically unstable, which is why we are not so familiar with them in our everyday lives. Then there's a bunch of neutrinos here at the bottom. Neutrinos are special particles. There's thousands of them flying through us right now at this moment. You don't realize it, because they very hardly interact with matter. This is why we don't notice them so much. And then there's some special particles here. These are force particles. They carry the fundamental forces. Now that becomes a bit technical, I know that. But you may recognize, for example, on the top here, the photon. The photon is the carrier of light, of electromagnetic radiation. So basically, you need just a handful of particles to describe all matter in the universe. That's a fantastic realization on its own. But it's also not completely right. Because it turns out, with these particles, you can only describe about 5% of the content of the universe. Only 5%. There's 95% of the content of the universe, which we don't understand today. We don't know what it's made of. We give it names, such as dark matter, a bit more even dark energy, but that tells you as much as saying, we don't really know what it is. It's dark, it doesn't shine light on us, or it doesn't reflect light upon us. But we don't really know what it's composed of. And so we have a lot of work to do to understand the universe. Then the question is, how do we then search for new physics? How do we search for new particles that could explain these phenomena? Well, we have many ways, but there is one very controlled way on Earth to do so, and it's through particle accelerators. And the currently most powerful particle accelerator on Earth is the Large Hadron Collider, the LHC. It's a collider which is located near Geneva. Geneva is here at the bottom of this lake. So it's on the France-Swiss border, and it's hosted by CERN. And CERN is the European research facility for subnuclear research of elementary particles. CERN is here. And so you see at scale the tunnel of the LHC there. So it's a circular particle accelerator, which is 27 kilometers in circumference, and it lies about 100 meters under the ground. In this tunnel, we accelerate particles, protons, and we accelerate them to extremely high speeds, extremely high energies, almost the speed of light, actually. And then, at 4 controlled points around that circle, we make these particles collide. And from those extremely high energy collisions, we then search for the creation of new particles. Now, of course, at these points, you want to build particle detectors, because you want to record these collisions and see what happens inside. So here in Belgium, we are collaborating on one of those experiments. It's called CMS, the Compact Muon Solenoid experiment. And it's a detector, and you see it schematically represented there. Now, I want to emphasize, in Belgium, we are very well represented in that experiment. There's about 100 people working, Belgian people working on the experiment, and some of them have very high-profile positions as well. So I wanted to emphasize that tonight. You see a sketch of the detector here. It's a cylindrical-shaped detector, and it has different layers. Each layer identifies different kinds of particles which fly out of that collision. And here you see an actual picture of what the LHC looks like. It's composed of many magnets. All these blue components are magnets. And these magnets are there to bend the particles, to keep them on that circular trajectory. Then there's, of course, components with electric fields. They can accelerate these particles up to these very high energies. And now I want to give you a few numbers. Numbers can be boring sometimes, but I assure you in this case they are definitely not. The magnets here are superconducting. That means you have to cool them down to extremely low temperatures for them to operate. These magnets, they work at 2 degrees Kelvin. For comparison, that's colder than outer space itself. So the LHC is the coldest place in the entire universe. On top of that, you need to operate these things in a vacuum. You don't want the particles to actually bump into air molecules. So you need to make a vacuum inside, and that vacuum is more empty than outer space as well. So it's also the emptiest place in the entire universe. That's amazing, and the reason I tell you that is not to show off. The reason I tell you that is because you have to realize that we have to work in extremely challenging conditions. And of course, if you work in challenging conditions, you have to innovate. You have to make new technologies which have never been built before. And so these state-of-the-art experiments, they're a perfect breeding ground for innovation. I've been talking a lot about these collisions. Here you get, after a while, a visualization of what that actually looks like. So you saw in the beginning these 2 particle beams coming in. They are collided at this given point. And from that collision, new particles, new matter can emerge. Now you may wonder why. Well, Einstein, he has taught us that E equals mc squared. Energy and mass are equivalent, and so they can be converted into one another. That's the principle also behind nuclear energy, but we also use it here in our fundamental research. And then you end up with an image like this. So here you see all these particles flying out of that collision point. I give you maybe another example to emphasize how complex and how dense these events can become, these collision events. And the reason why I tell you that is the following. The innovation that we have to bring into these experiments is immense. I mean, look at, this is the actual detector. You get an actual picture here, and you see here a human for scale. So these are very big detectors with a lot of electronics going in. On top of that, they don't have to be only very big, the detectors, or very complex. They also have to be extremely fast. We have to collide these protons, or we do collide these protons, every 25 nanoseconds. That means 40 million times a second we collide these protons. And 40 million times a second, we have to read out all these electronics, we have to process them, and we have to make very fast decisions because we cannot store 40 million events per second. That's way too much storage. So we have to make extremely fast decisions which of these collisions are interesting and which might not be. And that brings me to the following. I mean, the innovation does not only lie in hardware developments, it also lies in software developments. And something that has become very popular in the past decade is the usage of machine learning. These are computer algorithms which you can train or you can learn them to recognize certain patterns. And we learn them to recognize interesting proton collisions in our detector. Now, this brings me to a nice example, because of course we use existing algorithms from the computer science community, let's say, but we also develop ourselves innovative and new algorithms. For example, algorithms which are extremely fast, besides being also very efficient, and which we then implement on electronic units, which are called FPGAs, very close to the detector, so that we can make these very fast decisions. Now, these algorithms, developed at CERN, they also gain a lot of interest in industry, for example, in companies that develop self-driving cars, because they also need to make very fast decisions sometimes. And these decisions, they are based sometimes on life and death. So for them, it's extremely important. And that shows you a nice synergy between very fundamental research on one hand and the more applied research in industry on the other hand. And this is a question that we often get, and it's a good question. People should ask it. Why do you do that fundamental research? What do we get from that in our everyday lives? It's a good question, but I want to emphasize tonight that there is a lot of stuff which we use in our everyday lives, which comes out of the research at CERN. And your mobile phone is probably the best example. The touchscreen in there, it was first developed at CERN because we needed to operate these complex machines very efficiently. See here one of the very first prototypes. The World Wide Web, it also finds its origin at CERN because we needed to collaborate internationally, share those data with all the scientists all over the globe. Also in the medical industry, PET scanners find their origin at CERN. And also more recently, CERN is involved in a program for cancer treatment. They're helping with new technologies which are based on acceleration and radiation with heavy ions. And CERN has the know-how to do that. These are small-scale accelerators that accelerate heavy ions and that are aimed to, in a very targeted way, radiate the cancer cells. So all of these innovations, all of these new technologies, you get for the equivalent of 1 cappuccino per European citizen per year. And there you have your answer to the question. But I hope I convinced you tonight that this is very much worth it. But if you ask me personally, why would you pursue such fundamental research? There is one simple answer. It's human curiosity. Because I want to understand how the universe works. I want to understand how it was created, how it evolved, and how it came to what we see around us today. And the fact that we as humans can ask those questions, and on top of that we can even answer some of those questions, that's already amazing. And that to me is reason enough to pursue such fundamental research. Now, there's a million other things I wish I could talk to you about tonight, but I will be around after the event, so during the dinner, please come to me, ask me anything you want, and if you bring me a cappuccino, I will let CERN know you made your contribution for this year. Thanks a lot.